In this video, we're going to be learning about graphing using transformations, which is one of the most useful methods of graphing that we'll talk about. So before we can get started with the transformations, though, we need to talk about the parent functions. And there are 5 of them that we'll talk about in this section. We'll throw a few more in there as the course moves on, but for right now, we'll start with these 5. And to put the graphs together, in earlier coursework, you would most definitely use an XY table and plot some points. Now, I do want to be really clear. The idea here is to graph using transformations. So if you ever find yourself using an XY table, stop and go back to what we're learning right here. So we won't be using XY tables in this course or any others moving forward. So to get started, though, a lot of these graphs, these parent function graphs, you already know. For example, the parabola is the U-shaped graph. Looks something like this. The square root function, if you think about the domain and range, as we discussed earlier, you can see that it would be entirely in quadrant 1, as your x's needed to be positive and your y's needed to be positive. The cubic function would look something like this. And the cube root function would be similar to that, but it kind of appears to be more on its side. Looks something like that. And finally, the absolute value function, the one everybody describes the same way, that's your v. And we'll talk about why it's a v later in the course, but for now you can see the 5 different parent functions that we're going to start with. Of course, all of which could be checked by plotting a bunch of points, but certainly not something we're going to do. Now, also want to be able to track throughout this transformation process one specific point. All of the points that we're going to be tracking for these 5 parent functions would start at 0, 0. Okay? And for the transformation process, so that we can talk about all of the different types of transformations, we're going to use the y equals x squared function for all of these. I picked this one because most people are familiar with the parabola, and hopefully we can focus on the transformations as opposed to some weird looking graph. So the first type of transformation that we're going to talk about is a horizontal shift, which I usually describe as occurring inside the function. So let's look at a difference between y equals x minus 2 squared versus y equals x plus 2 squared. So hopefully everybody is seeing what I mean by occurring inside the function. So it's not a formal way of describing it, but it will hopefully be helpful to you. So the original parent function that we started with was the parabola that opened up, and as we talked about, the point that we're tracking is 0, 0. Well, the negative 2 and the positive 2 occurring inside the function take the original parent function and shift it horizontally. So this graph, with being a negative 2 inside, actually moves it over here to the right 2 units. And the positive 2 actually moves it to the left. So I missed my axis. There we go. To the left 2 units. Now, that might seem backwards, but you have to remember that when you do these types of problems, when you transform them, the point that you finish with, if we started at 0, 0 and after the transformation, the point that we finish with should be a point that is satisfied in the equation. So if I take this point and I go back into this guy, it should work. Notice if I take a 2 and plug it in here, my y value would also be 0, so we know we went the correct way. Similarly over here, if I take my x to be negative 2 and I plug it in, you can again see that the y is going to be 0. So it might seem backwards for the horizontal shift, but you're always able to check your point to make sure it is in fact has been moved the correct way. So now we're ready to discuss the vertical shift, which I a lot of times will describe as occurring outside the function. So maybe an x squared plus 2 versus an x squared minus 2. So different from the previous example, the plus and minus 2 here kind of sit away from it or outside of it. And this is going to be your vertical shift. And it says to take the original parent function and shift it 2 units either up or down. Now, in this case, the plus 2 means probably what you would expect, it to go up 2 units, leaving us with our point at 0, 2. And the minus 2 on the outside takes the original function and moves it 2 units down, leaving us with our point at 0, negative 2. And as always, you can take these points and plug them into the original and they should work. And I would always encourage that, especially when multiple transformations are involved. The next transformation we'll talk about will be a reflection. And to be really clear on this, this is a reflection about the x-axis. We'll have to mention a few other types of reflections later in the course, but for now, the reflection about the x-axis. So once again, the original parent function, y equals x squared, and if we put a negative out in front of it, that's going to be the reflection about the x-axis. So we'll take the original parent function and flip it over the x-axis, and now in this case it's a downward opening parabola, and our point doesn't change. The point is still at 0, 0. Now the final type of transformation that we'll talk about in this section will be a scalar. And now for the scalar, it's very important to start with the parent function, because this one is very difficult to represent, especially because we're not graphing in great detail by plotting a bunch of points. We're focused more on what a global graph might look like. So for this one, I do have my original parent function up here, and we'll compare it now to maybe y equals 2x squared versus y equals 1/2 x squared. So the way that these scalars affect the original parent function is that it actually controls the rate of which the graph goes up the y-axis. So if the scalar out in front of the function is bigger than 1, in this case it's 2, that's going to make it go up the y-axis more quickly, which makes it look like it's a little more narrow. Now I missed my mark here a little bit, but you get the idea. So this graph right here needs to visually look different than this graph right here, and so my graph of y equals 2x squared is going to go up the y-axis more quickly and therefore appear to be more narrow. Alternatively, the graph of y equals 1/2 x squared, this is where we're going to go up the y-axis more slowly. That scalar that sits out there is a proper fraction, so it's going to go up the y-axis more slowly, and it's going to make the graph appear to be wider than the original parent function.